Hi everybody. Today we're going to be learning about a new topic called waves. What is a wave? Is it this? Hi. Not necessarily. We're going to be learning about light waves, sound waves, mechanical waves, perhaps even ocean waves, and a lot of these types of waves behave using the same set of rules. So we're going to talk in general about all types of waves today and how we can understand their components. To start, we're going to look at three animations that all demonstrate wave-like motion. And I'll ask, what do all these three examples have in common, even though they're all going to be very different things? The first example is doing the wave at a sporting event. Looks like this. You stay in your seat until suddenly the wave reaches you, and then you stand up, and then you sit right back down. So there's an example of wave-like motion. Next, flicking a rope. You can imagine that black dot on the left is somebody's hand, and they move their hand up and down, and a wave pulse is generated, which moves down the rope. And the last example is going to be pushing against water in a container. Now, in order to picture this one correctly, you'll have to imagine that you're looking from a top-down view into a container of water, like a bucket or a pool or anything like that. And then imagine that you stick something flat, like a sheet of metal or cardboard, into the water, and then you push that flat sheet forward. What you'll be doing is knocking into the water molecules, which will then knock into the next water molecules, which knock into the next water molecules, and you get this pattern where each molecule pushes the next one. So in all three of these examples, there are two things I can identify that happen in common. First, some kind of disturbance travels from left to right across the screen, so something is being transmitted. But the second thing I notice in common is that the objects that make up the wave don't actually travel themselves. In other words, the people at the stadium don't get up out of their seat and move to another seat. That's not how the wave works. Similarly, the rope is flicked up and down, but we don't actually see the rope leaving that person's hand. And in our last example, each water molecule moves forward and then snaps backward and never actually makes it to the other end of the pool. So those are the things that are in common, and they get us a little bit closer to understanding how waves operate. One more thing before we move on from this slide. Each of these wave pulses is traveling through a unique kind of medium, which is going to be our word in physics for a certain kind of material. What is the medium in the first example? Well, the medium is people. That wave is traveling through a medium of people. That's the material that makes up the wave. Now, people isn't really a material we're going to talk about in class, but you get the idea. Number two, the medium is rope. That's the material the wave is using in order to transmit itself. And in the final example, that material is water. So we would say the medium that this wave travels through is water. So just get used to understanding that the word medium no longer means a t-shirt size, but in science it means a material that a wave is transmitted through. Moving on, a wave is defined as a disturbance that travels through space and carries energy. And I'm specifying in this definition that a wave will not actually transfer matter any significant distance. It only transfers energy. Here's an example of this. This animation is going to reset in a second and show a spot on the surface of a lake or a river or a stream. And let's say someone is splashing and sends a bunch of waves towards that spot at the water. Or maybe there's like a duck sitting on top of the water, and that could be the red dot. As the wave approaches, you'll see that duck, let's say, bobbing up and down in the water, but they won't actually travel any significant distance forward or backward as a result of those incoming waves. So again, that definition kind of makes sense here, that the wave is simply a disturbance. It's something that comes along and makes matter fluctuate, but never actually transports it from one place to another. So that's our definition for a wave. And again, as you can see in the animation, energy is being carried and transported by that wave, but matter is not. So if you look at just a single location within any medium or material, we'll see that the waves will always pass by without actually bringing the medium along with it. And again, at least not any significant distance. Some waves will actually move the medium forward and backward a little bit, like the pool example in the last slide, but not any significant distance. So again, one last thought here. Only energy has been transmitted. All of the matter is still in its original position. So with that basic definition in mind, I'm going to carry that definition forward onto the next slide here. I want to teach you two terms that are going to be very useful for you in terms of calculating properties of waves. This will be very useful when we study sound waves and light waves. In this animation, we're tracking that duck on the surface of the water that's bobbing up and down and up and down. And we could actually take a stopwatch or a timer, and we could time the amount of time that it takes for that duck to bob up and then down. Or we could do the reverse. Watch it when it's at the top and see how much time it takes to go down and then up. So we're going to start a timer on the count of go. And displayed on the screen is the amount of time that it took for it to go down and then back up. What we just recorded is called the time period. Usually we just say period. And we symbolize it with a capital T for time period. And that's defined as the amount of seconds needed in order to complete one wave cycle. What is the wave cycle in this case? It's one rotation of the object going down and then back up. Or it could be starting at the bottom going up and then back down. Either one of those could be considered to be the wave cycle. It's hard to really say where the cycle begins and when it ends, so we can arbitrarily choose any point as the beginning or end. So that's time period, and time period is actually relatively easy to measure. You saw we just did it just now, and all we needed was a stopwatch. So then what's the other definition? Well, it's actually the opposite of time period, and it's actually the more useful concept between the two of them, although it's a little bit more challenging to measure directly. It's frequency. Each wave has a certain frequency, and frequency is a word that you use in your everyday language to mean how often you do something or how often something happens. And this is exactly the same meaning, but applied to things that periodically repeat over and over again for wave motion. So frequency is defined as the amount of wave cycles that are completed every 1 second. So I could look at this duck bobbing up and down in this analogy, and I could start looking at the bottom, or I could start looking at the top, and I'm just going to choose the bottom arbitrarily. And I'll look at the bottom, and I'll try to figure out how many wave cycles it completes in 1 second. So I'll count 1 second on the stopwatch, and we'll see where we have to pause it after 1 second. So here we go. Ready, go. You know what? Actually, it's kind of tough, because unless I was a robot and could actually pause the video, and I could do that, but when you're doing experiments, you can't pause reality. Frequency is actually really hard to measure. It's probably some fraction of a cycle that we were able to do in 1 second there. Maybe we went up and then started to go down, but didn't quite complete it to the bottom. So anyways, my point is frequency can't be easily measured, but it can be calculated. If you look at these two definitions, period is the amount of seconds for every wave cycle, and frequency is the number of wave cycles per second, you might notice that these two definitions are opposites of one another. So that means that frequency can be calculated by taking the inverse of time period. If you take the number 1 in your calculator and then say divide by, and then plug in what the time period of a wave is, and then hit enter, you will actually get a number for what the frequency of that wave is. Time period is an amount of time, so it's measured in seconds. So what's the unit for frequency? This is something that's brand new. Frequency is symbolized by the letter F, of course, and the unit is actually the per second, which is a little bit awkward because per second is something that we usually hear in combination with other units. It doesn't really feel satisfying to say the per second all by itself. So scientists didn't like this either, and so they came up with a new name for the per second unit, and that name is a hertz, named after a scientist. So Hz is the unit for frequency. So I would say this wave has a frequency of that many hertz. All right, now that we know the first little bits of wave vocabulary, it's time to add in the last few pieces. In terms of if you're looking at a wave, how do you talk about the different parts of it? So we're going to get very visual here. I've got an illustration of a wave, and it's a continuous wave as opposed to just one wave pulse all by itself. So it goes on and on and on, and we could keep drawing it as long as we want to, but I'm going to stick with 3 humps on the top and 2 humps on the bottom just so we don't run out of paper. So what do we call these humps? Probably not humps, that's not a very scientific term. The top of a wave is referred to as the crest. That actually comes from a barnyard animal, which is the chicken. Chickens and roosters have things on top of their heads that are like red, and that's called the crest. And for some reason, scientists thought it would be an awesome idea to name the top of a wave, whether it's a sound wave or a light wave or what have you, after chickens and roosters. So there you go. The bottom of a wave is called a trough. And this is also related to a barnyard animal, the pig, because pigs eat out of troughs on farms. So you can think of the top and bottom of a wave each being named after a different barnyard animal. Who knew? The next term you have to know is wavelength. Wavelength is the distance from one point on a wave to the corresponding point on the next wave. You could also just think of it as the length of one cycle of the wave. So in this illustration, I've drawn the wavelength as beginning when the wave is in the middle. Sometimes we call that line going through the middle of the wave the equilibrium point. So that first green dot is at the equilibrium point, and then we watch the wave go up and then down and then back up to the equilibrium point, or back up to the middle. At that point, the wave is actually ready to start that cycle over again, and once again go up and then down and then back up. So wavelength is the length of one complete cycle of a wave. Now you can measure it from center to center, like I've done, but you could also measure it from crest to crest. Because again, it doesn't really matter where we consider the wave to begin or end, because it is a continuous object. It goes up and down and up and down and up and down forever, so there really is no beginning or end that you need to be able to identify. So just start and end it wherever you want. So if you start paying attention to this wave at the top of that first crest, then for one cycle to occur, that wave will have to go down to the first trough and then all the way back up to the next crest, and then we're ready to start the process over again. So that makes that distance also one wavelength. You could also measure trough to trough, and I bet some of you were wondering about that. So yes, that is possible too. And the last thing I'll note is that actually any of these green lines, including that random one I just added there, could work as one wavelength. So one wavelength can be measured and found out in a bunch of different locations. Just pick any random spot on a wave and then figure out on the next wave where that exact same spot is, and that's the wavelength. Wavelength has a funky symbol, which you can see right there. That is the Greek symbol lambda. Lambda is the symbol for wavelength because it kind of looks like a wave with a little leg attached to it. So that is wavelength. The final thing that you can visually identify about a wave is its amplitude. Amplitude is the intensity of a sound wave. It's how hardcore it is. So for a light wave, you could consider amplitude to be brightness. It could either be bright or dim. And for a sound wave, it could be volume. A really loud sound wave will have a large amplitude, and drawing a loud sound wave would look like very tall waves. And then a very quiet sound wave, like a little whisper like this, would have a very small amplitude, and the wave would look very short. Amplitude is something that you can measure on the page with a ruler if a wave has already been drawn for you. And you can either measure it from the equilibrium point up to the top of the crest, or you could alternatively measure amplitude by looking from the equilibrium point to the bottom. But one thing I must specify is you would never measure amplitude from the crest all the way to the trough. That would actually be double the amplitude. So remember that amplitude is simply measuring from the center to the top or from the center to the bottom. Don't let that trip you up. All right, now that we know all of the visual components of a wave, it's time to talk about the two different categories of waves that exist. And now that you have that vocabulary in your back pocket, you'll be able to identify these really easily going forward. There are two different types of waves, and the first type I'll describe to you is called transverse waves. It's a big word. Transverse means this. So let's just take a second to take in this visual here. We have one example of a transverse wave up on top with the blue dots, and we also have this kind of nice two-dimensional plane which is rippling, and that is also a transverse wave. So two different, completely unique visualizations of the same concept. So what do you think makes this a transverse wave? Here's what makes it transverse. You'll notice that both waves, the blue dots and the grid, have a wave pulse that is traveling from left to right across the screen. So you can see what direction the wave is moving. However, if you pay attention to any blue dot or any vertical grid line, you'll actually notice, if you look closely, that the material that makes up the wave is not moving in the same direction as the wave. They're actually going in completely different directions, a perpendicular direction, you might say. So here's the definition for a transverse wave, and this will explain what you're seeing. The wave's medium in a transverse wave will always move perpendicular to the direction of the wave's travel. It's a hefty definition, but it's basically saying if the wave is going left to right, then the medium, the material that it's made up of, will go up and down instead. Now, this might seem counterintuitive to some people. If you splash your hand into some water and you see the wave move away from you, your intuition might tell you that that water is actually traveling further and further away from you. But looking at this right now, you can see that that may not be true if water waves are in fact transverse. So we'll talk more about water in a little bit. The second type of wave that you'll encounter out there in the big bad world are longitudinal waves. A longitudinal wave looks like this. So let's take a second to take in the visual. Try to think about what we're seeing here. This is actually a lot like the example we saw at the very beginning where we described 3 different types of wave motion. This was like the example of pushing water in a container. Ooh, so we're getting a little bit closer to understanding how water works. So this is a longitudinal wave. What do you think makes this longitudinal? Well, let's take a closer look. It looks like the wave fronts are moving from left to right across the screen, just like in the last example for transverse waves. And if you look really closely at any of those red dots that are being highlighted, just so you can more easily pick them out visually, you'll notice that they are moving along the same axis as the wave front itself, but they're only going a little bit forward and then a little bit backward, and they snap right back to their original position. So what makes a longitudinal wave longitudinal? Well, it's about the wave's medium or material moving parallel to the direction of the wave's travel. Remember the previous example, let me go back for a moment. I know you probably want to write that down, but I'll go back for just a second. This was a transverse wave, and that type of wave had its medium moving perpendicular to the wave itself. And you'll notice that there's an underline under the 2 S's in the word transverse. That's because it's a hint for you to remember what type of wave is which, that the word with 2 S's in it looks like the S-shaped wave that you picture when we think about waves. So that's a hint to help you out later. Is transverse is the wave that looks like an S. And then the second one was longitudinal, and I underlined the 2 capital I's in this word because longitudinal waves usually look like a long stick like this. They're not as curvy. So that's a longitudinal wave, and again, this definition is just like the last definition, but it only changes by 1 word. I've taken out the word perpendicular, and I've now stuck in the word parallel. So for a longitudinal wave, if the wave is moving left to right, then the material is also moving left to right. And now you know the 2 types of waves, which means you can now answer this question. Between transverse waves, which look like S's because they travel one way and oscillate another way, and longitudinal waves, which travel one way and oscillate in that same orientation, between those 2, which one describes how sound waves work? What you're looking at here is a speaker that is emitting sound waves, and each of these blue dots represents an air molecule. Is this a transverse wave, or is this a longitudinal wave? Think about this for a moment. So this is a longitudinal wave because you can see the wavefronts are moving outwards away from the speaker, and you can see that individual dots are also moving away from the speaker and then snap back towards the speaker once again. All the motion is happening in the same direction here, which is outward. Outward and inward, to be more specific. There's no dots here that are going like around in a circle around the speaker. So this is longitudinal. So now you know, sound is a longitudinal wave. So when I make this sound, the reason that reaches your ears is because I just vibrated air molecules in this room, and each air molecule knocks into the next one, and that signal was received by my microphone, and then through complicated means, my microphone has now sent information to your device, which is now playing sound out of a speaker, and that speaker is knocking into air molecules, which knock into other air molecules, which knock into your eardrum. And then we'll talk more about how the human ear works later in this year. So sound is a longitudinal wave. That's our answer. What about light waves? You may have seen this animation before of light being split by a prism, and they look kind of curvy and S-shaped, so maybe that gives you a hint. So is light transverse, or is light longitudinal? Let's think about that for a moment by looking at this animation. The answer is light is a transverse wave. And you can tell just from the animation that the waves are traveling to the right, but the waves have crests and troughs that are oriented upwards and downwards. So that is a perpendicular direction to the waves' travel. So that must mean light is transverse. All right, moving on to our final question here. Here's an animation of a water wave. So this is like you're at the beach and you see the waves slapping against the sand. And you look out maybe like, 20 or 30 meters, and you see these waves coming in towards the beach pretty evenly. Is this a transverse wave, or is this a longitudinal wave? Go ahead and pause for a second and think about it. Well, if you notice that these little circles are representing the motion of one individual water molecule, then you'll notice that as the wave fronts move from left to right across the screen, the individual molecules are moving in the same orientation, left to right, but they also move in a perpendicular orientation up and down. So that circular motion is both. So that's actually our answer, is water is a combination of transverse motion and longitudinal motion. And if that feels like an unfair answer, that's because it kind of is, because I didn't tell you that was an option. But if you guessed that, well done. Water is actually a combination of the two. So I hope this gave you a good introduction to waves. I hope you can now use the vocabulary you picked up today to move forward in the class and feel confident as we get into the harder things about waves that make them more complex. There's a lot of really cool stuff coming your way. So hope you're looking forward to that. I certainly am. I'll see you in the next video.